I previously did a video about Navier-Stokes and one on the Riemann hypothesis. And the nice thing about those two is I think it requires, especially the Riemann hypothesis, very little mathematical formalism to at least understand the question. Of course, it requires an extremely deep amount of mathematics to start appreciating the machinery that's required to solve it. However, if we are moving on to the Yang-Mills equations and the Millennium problem that has to do with quantized Yang-Mills equations, there's actually quite a bit of mathematical understanding you need to have to even understand what the problem is. And so I wanted to take this as an excuse to foray into basically all the mathematical machinery that underpins modern physics. What is a good way to kind of go about this? I don't think we can really cover it in one video, but I can try to give a little flavor of the formalism that's required, a beauty that you can motivate trying to go through this curriculum in more detail. So Yang-Mills. First, I guess we need to actually understand some notations. We do want to have foundations, geometers, foundations, Yang-Mills theory, Yang-Mills equations, maybe just like even be less ambitious, just equation. So one is we can look at just notations, right? And I don't kind of, I'm doing this with no prep. I kind of really want to take you learning with me with the help of AI, and hopefully as a meta process kind of inspire you to use these large language models to delve deeper into technical subjects that you wanted to study but haven't really kind of had the time or maybe even the motivation to pick up yet. Okay, so we'll start with objects and conventions. So manifolds that we care about in the study are smooth-oriented n-manifolds, and you assume a Riemannian metric. So maybe something that we can use, Grok. Hey Grok, so I'm just going to need your help in defining more precisely certain mathematical objects that I care about. So for instance, a manifold that is required in studying gauge theories, so they have a Riemannian metric and they're smooth and oriented. I need you to define for me what an oriented n-manifold is. Let's start with that.
An oriented n-manifold is a smooth n-dimensional space where every point has a consistent handedness, like always picking left over right, so you can define a direction everywhere without flips.
Okay, great. Can you define it mathematically?
An oriented n-manifold mathematically has a nowhere vanishing n form, like a consistent volume element, where m equals m omega, such that integrate m omega gives a signed measure over any compact region.
Okay, but tell me, what is it? Is it defined on what space? Like, let's actually like write out the definition formally first.
An oriented n-manifold M is defined as a smooth n-dimensional manifold equipped with a consistent choice of orientation, meaning a global reduction of its structure group to GL plus n, rational, the part with positive determinant. Formally, for every point P and M, you fix an equivalence class of bases in the tangent space TPM, where switching order flips the sign, like choosing right-handed versus left-handed screws everywhere. The key is that the transition functions between coordinate charts have positive Jacobian determinant. Picture a sphere. Every little patch gets a north-south roll, so arrows never twist oddly as you move around.
Let's use the sphere as an anchoring example again.
Take the two-sphere, S2, as our oriented n-manifold with n equals 2. Cover it with two charts, one centered at the North Pole using spherical coordinates, theta, phi, where theta is collidative, from 0 to almost pi, and phi is longitude, from 0 to 2 pi. The other chart flips south-north. The transition between them, say from north to south, has a Jacobian determinant that stays positive, like +1, ensuring no orientation flip. At every point on the sphere, pick a basis for the tangent plane, like one vector along meridians, another along parallels. So swapping them always gives a negative sign consistently everywhere. Think of it as the sphere remembering clockwise
So
is
stop.
positive,
Stop.
no matter where you stand. You can't accidentally turn it inside out without breaking the rule. That handedness locked across the whole surface.
Okay, so she started with a pretty, I think, simple example that we can visualize, the two-sphere. And of course, on the two-sphere, you have this tangent space, which is saying that regardless of how you choose the basis, you're able to express something that has handedness, so there's an orientation. Can you now go on, Grok, about slow down and tell me more about this example?
So here's the sphere again. Two-dimensional manifold S squared. Pick any point, not the poles, on the equator. Say, the tangent space there is just a flat little plane, and you choose two vectors, east and north. If you take their determinant, like their cross product, it gives you an up arrow sticking out. Orientation means every other patch around the globe must agree on up. So as you walk around, dragging your east and north frame, the up vector never flips. It stays up. Not like a Möbius strip, where halfway round, you're suddenly south-facing. Gauge theories love this, because when you compare frames, like in electromagnetism's connection forms, you need to know, did I rotate positively, or did I sneakily reflect? Orientation keeps the sign honest.
That's really good. I'm having trouble drawing a Möbius strip. So, the easiest way to do that in the math sense is to say that this is connected to this. So the point that Grok was trying to express is that in the case of a sphere, which is actually an oriented n-manifold, there is an orientation that stays consistent depending on how you define this basis in a continuous manner. So it's just like it's like a mathematical formalism of a physical space
So on the sphere,
that we are familiar with.
Comes from gluing those patches smoothly.
Yes, that's right. Can you stop for a second? Okay. So as I was saying, what's really nice is that usually the mathematicians, or at least some mathematicians would agree, that the motivation for formalizing these objects is coming from physicists. And so in this case, the physicists care about spaces that we are familiar with, right? Spaces that we can find in nature. And so some of these properties you'd want to extract and then formalize and study. And so oriented n-manifold, M, is the abstraction of some very familiar spaces. For instance, this two-sphere. Two-sphere, keep in mind, is you're really taking the two-dimensional manifold. That's the sphere. So this is the two-sphere. Not really writing this. This is two-sphere. If I were to write this correctly. And so what I'm showing you is a tangent bundle, or actually no, just the tangent space. And it's a little bit hard to see, but I am defining this tangent space with the basis expressed by the north facing vector. So obviously this is an R2, so this is expressed as 0, 1, and 1, 0. And if you take the determinant of that, you'll remember that actually gets you a vector that juts out into an orthogonal direction. And so that's what's represented by this yellow vector. And I'm writing the orthogonal stuff here, showing that it's coming out of the tangent space. And the point is that you can continuously glue these patches. There's a way to obviously define this tangent space for an approximation of the infinitesimal space around this, any arbitrary point on the sphere. And as you move that, there's this yellow vector will always be pointing this direction. There's no point if you even take it around, the full circle and move it back. I use this red thing to indicate that. If you move it back, you can imagine continuously it will face this direction. And you're like, okay, well, that seems very natural, but this is actually not true of all compact and manifolds. It's not true of the Möbius strip, because you can define this tangent space, for instance, in the same way. And the property of the Möbius strip is that you actually do switch signs, because it's actually kind of contrived, maybe example, the sense that if you are letting it slip in this direction, goes this way, then you glue it in a way that actually it goes inside. So it's kind of hard to see with this drawing, but basically the tangent space now will have, based on how it's glued, so then it comes out this way, but here instead of pointing this direction, it's going to point this direction, which means the determinant is making the yellow thing point inside, and so you've now flipped the orientation. So this is not true. It's in particular of non-oriented compact manifolds, of which in at least a two-dimensional case, the Möbius strip is an example. Is not in oriented two manifold, compact two manifold. Okay, so why do we care? Well, we want to practice physics where, at least in our reality that we're familiar with, orientation actually is a preserved quantity. Okay, so that's cool. So now we know these are the structures we care about. We can move on to forms. So G-valued K-forms on M. Operators, exterior derivatives. Hey Grok, thanks. So now we want to move on to defining forms. G-valued K-forms on our compact-oriented manifolds.
G-valued K-forms are sections of the bundle of anti-semi-invested K-linear maps on a compact-oriented manifold M. Basically, functions that take K tangent vectors at each point and spit out a G-valued number, like a Lie group element or algebra vector, flipping sign and vector swap. Think gauge theory. On our sphere, a one form could assign to every...
So that was quite a mouthful, so let's actually write that down. So G-valued K-forms. They're defined on this manifold, which remember is a let M be a compact oriented n manifold. You know what that means because you have the orientation on the tangent defined, and now form. These forms are omega k, so it's a G-valued K-forms on M. What is G? G-valued K-forms. Go back to what a G-valued, what the G represents.
G is just a Lie group, like U1, SU2, or their algebraic-like vectors instead of matrices. On the manifold M, think of G as the gauge flavor.
So now we have to remind ourselves what a Lie group is. So I would like you to help remind us what a Lie group is.
It's a continuous symmetry group where you can slide smoothly like rotating a sphere or adding angles. The smooth version of adding numbers or matrix multiplication, but as a space you can walk on.
So that's great. Can you give us an anchoring example while I write down the definition? Like,
for electromagnetism, G is U1. Think unit complex numbers, e raised to the I theta. So a U1 valued one form A on your sphere is like a tiny dial at every point, say the electromagnetic potential.
Sure, that's fine, but I want like a geometers one. So let's give me some more examples.
Okay, picture a three-sphere, S3. It's four-dimensional, oriented, compact. Now slap on an SO3 valued one form. At each point, give every tangent direction a little 3D rotation matrix. In gauge theory, that's like a local compass for spin or angular momentum. Another, the torus, T2, two copies of a circle. Put an abelian G on there, say R2, and let your K form be a constant, say dx on dy.
So I would like to talk about Lie algebras, or actually, sorry, Lie groups, and I want to just give some examples of Lie groups. So for instance, ones that I can draw on a blackboard. It doesn't have to be two-dimensional. Okay, as it's visualizing that, let me try to actually start drawing what I think it's talking about. So S3 is the 3 sphere, and so we can't really imagine that, but you know that just based on the dimension, it's not just a tangent bundle that is, or sorry, a tangent space that is a two-dimensional thing, but it is a square, or sorry, it is a cube. And so you will need a basis that is now expressed by 3 vectors. And you can imagine a set of linear transformations on that space. Those linear transformations are, of course, a group because they satisfy the group properties. And so in this case, they're saying the linear transformation that physicists care about is SO3. So let's see. Okay, well, SO3. So solid ball, antipodal boundary points, rotation matrices multiply, so rotations in R3, SO3. So any rotation, right? Any rotation of the space. So rotation, now think about rotation is just a mapping from the space to the space. So I have this mapping. So SO3, so an element of SO3, so let's say, I don't know, X, which is an element of SO3, so then X, let's call it big X, or actually what are we used to? We're used to talking about this in terms of matrices, so let's just call it A is an SO3, so then A, maybe we'll take, rotate it just like this way. And so A will take an element, A will take any vector in this space, I'll make it to another vector, so it takes R3 to R3, and it's defined by, as you know, matrices that define this rotation. So what do you do with that one vector? You multiply a matrix, and then you get another vector. So that is a group, because every rotation has an inverse rotation. You rotate it this way, the intuition needs to rotate it back. Two rotations composed together get to another rotation. So that's one example. Things that also physicists care about, SU2. Let's see. Other ones that might be interesting to draw. Redefine Lie group, and why do we care in the context of gauge theories?
A Lie group is a continuous group. Points aren't just labels, they multiply and slide smoothly, like angles or rotations of a book on your desk. Why care? Because in gauge theories, forces like electromagnetism aren't scalars, they're symmetries. A Lie group is a manifold G that's also a group, so multiplication G times G turns G is smooth, meaning tiny shifts in position give tiny shifts in product. Algebraically, multiply near the identity E, say equals V equals W, and it looks like the Baker-Campbell-Hausdorff formula, log, except V equals W, divided by 2, plus minus the commutator. The commutator turns G into an algebra, the Lie algebra, and that's the engine. It encodes all continuous symmetries. Gauge theories just ask, what if space-time isn't flat, so those symmetries vary point to point? Then you need a connection, a form taking values in that Lie algebra to tell you how to rotate as you move.
Okay, relate it back to the manifold, those compact oriented manifolds that we were talking about.
Your compact oriented manifold M, like the sphere or the torus, is the stage. The Lie group G is the symmetry you want to promote from global to local. At each point on M, you attach the group. So instead of one big rotation for the whole space, every tiny square mile gets its own private copy of G. Then the G value,
I can stop it here.
Call it A.
Yeah. Okay, sorry, we actually have to go back to the forms because we were defining the form omega.
The G-valued K form omega is a section of lambda K Tm TOS G sub pole. Back K tangent vectors at P. Contract, get an element in the Lie algebra G. On the compact oriented M, That means you can wedge it with the volume form to get an L2 inner product. Integral m omega amanda m is real
Kind of
and
love
positive
this, by the way.
like kinetic energy of the field.
Okay, so again, I really require you to, because like when I learn math, so much formalism, but we're not anchoring it onto a physical object that we care about.
A g-valued one form is a map that, at every point P,
takes
one and spits out an element of the Lie algebra.
I don't know any physics, so I want you to give me this in a geometers example, like things, objects I know about. So I was talking about S3. If we're going to talk about wedges, you have to define it. So just like start from that.
Start here. The torus, T2, is your compact-oriented manifold, two circles glued smoothly, like a donut without seams. It's 2D, so its tangent space at every point is R2, one vector around the hole, one along the two. A wedge? That's just the antisymmetric bilinear. Take two vectors u, v. If I swap them, the wedge flips sign. So the two form, let's call it OMA, eats both directions. OMA u, v, divided by g value times area, like if g is real numbers. OMA equals dx anti-dy, means signed rectangle. And since the torus is oriented, dx anti-dy never switches from positive to negative. Picture.
Okay, so we're going a little fast, and then also I need to draw this, so we're going to erase this. Okay, so I'm going to draw a torus, and then you're going to go over that again for me. So the torus is a compact manifold. Okay, go on. And what else do I care about?
And what else? Well, once you have that omega, you care about curvature F.
Okay, cool. But let's like go back to defining omega.
That's how much your parallel transport fails after you loop back. On the torus.
Yes, I do love that. But do go back and explain to me what omega is and how to define it on this torus, the specific example.
Okay, back up. On the torus, omega is a g-valued one form. So it's not the wedge yet. Pick coordinates. Let theta go around the tube, theta around the hole, both from 0 to 2 pi. Then omega goes a theta d theta, a theta d theta, where a theta and a theta are smooth functions that spit out elements of the Lie algebra, like constant matrices if it's a flat connection, or maybe a theta over 2 pi times a fixed generator. So when you loop theta, you rotate by exactly one full turn. Geometrically, at each point on the donut, d theta is the unit vector along the tube, d theta along the circle. Omega tells you, if you step one unit in theta, how much symmetry rotates. That's your gauge field. The wedge only shows up when you exterior derivative. So that's omega. Two maps, a theta p and a theta p, taking tangent vectors and handing back g, smoothly, no jumps.
Okay, I'm trying to talk about two of these. This is, keep in mind, on the back. So then if you go around this way, this is how you orientation. No. Yep, because it's on the surface. Move this way. And then this is our tangent space. So this should be, I mean, this is obviously going to preserve orientation because we chose a oriented two manifold. I missed what Grok was saying. Sorry, Grok, can you just go back? I don't even know what omega is right now. So we care about what? How many?
On the torus,
yep.
Omega is just this. Pick any direction at a point, say along the donut tube, and omega tells you a number, or rather a Lie algebra vector, representing how much gauge symmetry gets charged when you move one step. Write it as omega equals A d theta plus B d theta, where d theta and d theta are like the x and y directions, but curved. A and B aren't scalars, they're in your G. So if G is rotation.
What exactly is this measuring? And can you, because I thought this was defined on the Lie algebra, so what Lie group and Lie algebra do we care about?
Infinitesimal twist, how much the internal symmetry changes as you slide along a curve. Yes, it's Lie algebra valued. Omega V is in chain, not D. So on the torus.
Oh, sorry, what Lie group are we talking about in this torus? Just like
our Lie group is SO3, so the algebra is 3x3 skew matrices.
Wait, no, it's not. SO3 is rotations in R3.
Right. SO3 is rotations in real 3 space.
Sorry, then we're talking about a one torus then, because this is the torus, the manifold is a two-dimensional compact manifold.
No, the torus is still two-dimensional, 2 coordinates, 2 tangent vectors, one along each loop. But SO3 isn't acting on those 2 directions. It's acting inside the fiber, on some internal 3 vector you carry along. Like, imagine every point on the donut has its own tiny gyroscope. Omega
okay, thank you. This is actually very helpful. So why do we care about SO3 on the tangent space? How does that even act on the tangent space of the torus?
It doesn't act on the tangent space. That's the key. SO3 lives on a separate fiber. The manifold gives you position and direction.
Okay, so it's defined on the fiber. Okay, so you didn't actually explain to me what a fiber is.
A fiber is just the private space attached to each point, like at every spot on your torus. You've got a little closet, and inside it lives the whole SO3.
Okay, so that means you can define an arbitrary fiber for any space. It could be as big as possible. So what is the physical motivation? What are these fibers? Are they, why do I care about that?
Yeah, exactly. Any fiber size, no limit.
But you didn't actually define a fiber. So I think you have to actually define what a fiber is for me.
See, a fiber is the extra baggage. Imagine the manifold as a bunch of points, each with its own private copy of G the Lie group.
I want a formal definition of a fiber. I want the formal definition of a fiber.
A fiber over a point P in your manifold M is the slice thick's P, then FP equals things attached to P, and the total space is M times F. Topologize so paths in M drag their fibers along smoothly. Formally, if it's a principal G bundle, the fiber is a right G torsor, basically G itself with no preferred zero, no vectors yet, just group. Like for EM, fiber at P is all possible phases U1, and moving changes which phase you pick. That's the gauge, not arbitrary size. Size is set by the symmetry you need to hide.
Size is set by size. Yeah, exactly. So thank you. Can you motivate then for me what a fiber is in, say, current physical theory?
In current physics, the fiber is the hidden variable, like in quantum chromodynamics. Each quark isn't just here, it's here and red, but red isn't a color. It's a label in the SU3 fiber. Move the quark a tiny bit, the color can rotate via the gluon field. Omega.
Okay, so is it fair to say that a fiber is another quantity that is a property and has to satisfy certain smoothness conditions? And so that's why we have to...
Yeah, pretty much. The fiber is just a state like, which phase am I in? Or what spin direction? But attached rigidly to position. So if I wiggle space, it wiggles too, but smoothly. Smoothness means no kinks. The way the fiber rotates as you cross the torus isn't jerky. It's C infinity, like temperature fields on Earth. That smoothness lets you write derivatives, your d omega, and so curvature appears. Without it, no consistent physics.
Okay, that's cool. So I guess we were defining omega. So omega, can you repeat for me, how does that involve fibers again?
Omega isn't the fiber, it's the elevator. The fiber is your little group copy at each point. Say a circle for U1. Omega says, when you walk on the torus, how do you rotate from this circle to the next one? It's like a rule for matching up fibers along an edge, without ever seeing the total twist. So no fiber, no omega. Omega only makes sense if there's something above to transport.
Okay, so then define for me what omega is then. What is this K form? And how does it involve both fibers?
Omega is a K form. That means it's a smooth machine that, at any point, takes K little arrows, tangent vectors, and spits back a Lie algebra element, antimetrically. So swap any two arrows, answer flips sign. On your torus, if K equals 1, omega x is a negative x, where x
Okay,
is
sorry.
the velocity, and
Step
A
back.
is your connection 1.
I don't understand why. So does K have to do with the dimension at all? Or does it have to be the same number size as the basis? Or it doesn't matter? Like, why do we care about these K forms? How are they being used in gauge theories?
No, K doesn't match the manifold's dimension. That's the point. Your torus is two-dimensional, but I can have a 0 form, just functions, 1 form, vectors with G values, 2 form, areas with G values, even 3 form, if I want, it just vanishes by antisymmetry. We care because physics lives in the middle. K equals 1 forms are potentials, like A in electromagnetism. K equals 2 forms are forces, like B field, strength squared. The wedge lets you pair them. FDA, a 2 form, tells energy. Dimension limits what integrates. A 3 form on 2D torus is 0, useless. So K is your toolkit. Pick what matches your symmetry and your equations.
Why do we care about these K forms again? Or rather, let's go back to gauge theories now that I understand what a Lie algebra, a Lie group is, a K form, also this manifold, all these definitions. What's next? Actually define for me what a gauge is and gauge theories are.
A gauge theory is physics where you start with a symmetry, a Lie group G, and let every point on your manifold declare its own private copy, but without saying which copy. The gauge is picking, at each spot, which copy is mine. You can shift all of them at once, a gauge transform, and laws don't care. Like on the torus, if G is U1, picking a gauge is choosing a 0 phase at every point, like setting every clock to noon. Omega, the 1 form, says how fast clocks desync as you walk. Curvature, F is real. 2 clocks drift apart even after you loop. The theory's point? F stays gauge invariant. Forces emerge from that drift. No hidden variables, just geometry of who agrees with whom. That's the whole game.
Okay, that's super interesting. So anchoring it back to some basic physics intuition. So on a torus, the gauge will not agree if we kind of go in a circle. Like, can you explain more about that? Okay, so
like
what does
if
it
you walk
measure?
around the torus hole and come back, your clock might be 5 minutes off from mine, even though we started together. That offset, that's curvature. Gauge says I can reset all clocks by the same amount, but I can't make your 5 minutes disappear. That's real physics. It's the same reason gravity isn't gauge. You can't redefine distance everywhere to make a black hole vanish. The torus keeps it tidy because it's compact, no infinity, so drift adds up to an integer, like quantized flux. That's why gauge theories on manifolds give particles, not just forces.
Okay, that's actually really delightful. Can you repeat all that? I want to absorb that better. So you're measuring some difference, and this drift in time, like how does that reflect? It's like it reflects curvature. So this is especially when geometry, the curvature and geometry.
Exactly. The drift is curvature. On the torus, if I carry my phase around the big loop and come back shifted by pi, the field strength F must be non-zero, because F measures exactly how much phase you gain per unit area. It's like the Earth being round. If I walk a closed circle and my compass points left instead of right, it's because space curved. In gauge theory, the geometry isn't just the torus shape, it's the fiber shape. SO3 twisting as you go. No drift, flat connection, trivial bundle. Drift, you're a non-trivial topology. Instanton sector, energy stored, like twisting a rubber band. That's why we obsess over bundles. They make time, space, and symmetry all feel the same bend.
Okay, so what is an interesting gauge theory then? Give me an interesting gauge theory and give me an interesting example of a math result
One
that
killer example, the Dirac monopole. Take our sphere S2 as your manifold, compact, oriented. Set G equals U1, so Lie algebra is real numbers, just phase. The one form omega makes it 1 minus cos theta d phi. Yeah, it looks weird, but as you walk north from equator, omega tells your phase to creep up slowly. South, creep down. Curl it, take exterior derivative, and you get f of sin theta d theta and d phi, the volume form. Integrated over the whole sphere, 2. That 2 is the magnetic monopole charge. But here's the gauge twist. At the North Pole, omega blows up. Can't define it. So you patch. Use 2 charts, north and south. On overlap, the difference in omega is d phi, which is closed, but not exact. Means the fiber bundle's twisted, like a Möbius strip in disguise. Physically, one particle leaking flux out the north, in the south. You can't untangle it. Gauge theory says it's real. Cool, right?
Okay, let me see if I can get some appreciation for that. So you're saying that the theory is able to precisely measure this type of like torsion. I don't know if that's the right word, because even if the space on which these things are defined is, pretty oriented, compact manifold, the way that you are defining these.
Yeah.
Oh, okay.
So what you're measuring isn't torsion. That's like twisting of the manifold itself.
Yes.
Levi Civita hates that. Here, the twist is in the fiber. On the sphere, the monopole makes your phase crawl no matter how straight you walk. Orientation keeps it consistent. North is always north, but the gauge chooses whether the crawl is clockwise in phase space. You measure it by asking, go around a latitude, do I return shifted? If yes, monopole. If the manifold were unoriented, like Klein bottle, you couldn't even define clockwise.
And so, sorry, is the physical intuition is like this one form is measuring something about magnetism, and it's because of this, there's a singularity in how the magnetic field is defined on this, on S2?
Right. The one form omega is exactly the vector potential A for a monopole. Around it, magnetic field B, curl A, but near the pole, A diverges, so B looks like it spikes from nothing. That singularity, it's fake. You patch with another A prime on the south side. Difference, A minus A prime, makes 2 pi times the circle.
Okay, so what is the intuition for why the bundle is twisted then? Like the twisting is happening. I guess the point is that there could be work done, and you're not losing it if you kind of go and.
Yeah, like if you move a charge around a monopole loop, the work integrate A dx is 2 pi g times integer, quantized. You might think, oh, it blows up at the pole, so you lose energy. But no, because of the 2 patches, the real field F stays bounded. The work is conserved, topological, not dissipated. The singularity is an artifact of picking which sheet you're on, like cutting a circle open to flatten it. But the physics is whole. That's why gauge theories love compact spaces. No edges, no leaks. Everything closes up.
Okay, so I'm already recording for very long, so I want to kind of get to some motivation for Yang-Mills. So you've defined for me a particular gauge theory. Can you motivate what the Yang-Mills equations are?
Yang-Mills isn't special. It just turns that monopole trick into a soup. Instead of U1, take SU2, double the fiber, non-abelian. Now parallel transport doesn't commute. Carry a spin up quark left, then down, versus right then down. You end up in different gauge. Curvature F of d omega, omega wedge omega, so self interacts. On flat space, that means gluons carry color charge, stick together, confine quarks. On a curved manifold, like S4, instantons pop up, tunnels between vacua, explaining why proton spin isn't just 3 quarks. The innovation? You started with geometry, ended with why matter holds. No electromagnetism, no gravity, just twisted fibers, and suddenly the universe has mass. That's the payoff.
Okay, so I think this is going to take quite a bit longer. So let's cut it off here and revisit in part 2. Thanks, Grok.